wanted to, I just wanted to introduce a different kind of motion. We talk so much about motion in a straight line, and we actually derive some equations that govern the motion in a straight line. However, I want to introduce to you circular motion, right? And we're going to concentrate on the very basics, right? That's how you hear the term uniform circular motion, because that's easy to understand, right? So they're explaining it there. Now, when we talk about uniform circular motion, we're really talking about a body that is moving around a certain point in a circle, but with constant speed. That's why we say uniform circular motion, right? We don't want to complicate it and make the speed around this point variable, or else things get very, very complicated, right? And here, well, the little diagram there has a V, and that is referring to the linear velocity at this particular point, right? You will be introduced, and maybe I should mention it here, right? There's also something called angular velocity, right? Let me just put that here. It's like this, right? Omega. And basically, right, it's the angle that has been swept out from one point to the other on the circumference there, divided by the time it took, right? So let's say you were to move from this point here to that point there, right, on the circumference of this circle, and you have swept out theta degrees. Oh, sorry, wrong. Whenever you're dealing with circular motion, theta is measured in radians, right? Radians. And I want to mention that radians is a different way of measuring angles, right? So I'll explain a little bit about radians in just a moment. So the angular velocity, omega, is equals to theta over time, where, as I said, theta is the angle swept out there, right? That angle, and the angle is measured in radians. Now, just what is radians? I warned you that sometimes these things will go too deep, you know. Really, when you talk about radian measure of angle, you're really talking about this. But if you have an angle in here, this circle is of radius r, and the line segment from there, not line segment, the arc, sorry, is L. Then the angle in radians is equal to L over R, right? Angle in radians is equal to the ratio of the length of the arc over the radius of the circle. And it's measured in the angle, theta is measured in radians, right? So if you write 2 radians, you write 2 with a little c, right? A little c. I think the c means circa, right? I have a little bit of history why they don't call it. You know, you probably use R there, right? They use c instead, right? Yeah. You will get to understand. Huh?
So we calculate with the angle equal L.
This is the angle in radians. If you want to know the angle subtended in the middle there, it's the ratio of the length of the arc over the radius of the circle. Right, so a little bit more, okay, I'll come to some comparison between radians and degrees just. If you are writing an angle in radians and you write it in terms of pi, You don't have to put a little c on top there. There's no need. So if you write 2 pi, people will know that you're talking about 2 pi radians. No need to put c. No need. No need. Right? And if I am to let's do a little bit here more. Pi radians is equals to 180 degrees. And this relationship now you can use to convert degrees. Like if you want, all right, from this, 1 degree is equals to pi over 180, right? So you want to know how much is 30 degrees, you just multiply by pi over 1, right? You multiply it by 30. You want 60, you know to multiply. And similarly, from that same relationship, pi equal 180 degrees. 1 radian is equals to 180 over pi degrees. So you want to know how much is 2 radian, 3 radian, and so on. You just multiply, right? So I warned you, you know, these things here a little complicated, a little beyond what you learned at CXC and so on. So before you can do the physics that you know involve these things in real detail and a certain level of complexity, it's important that you do some mathematics, right? Before you come and do the physics, right? So that is why I think some of the students, they do like analytic geometry and trigonometry. I think there are some other courses. Calculus. I think one of the girls show up with a formula earlier. F equal V times dm over dt and all of that. And that's beyond this course. Good. So they're telling you that the body in circular motion, it has a certain speed, right? Going around in a circle. And it will make a radius of, well, depending on how far the body is from the center of the circle is going around. Now, one of the things about it is that even though it's going around with constant speed, even though it's going around in constant speed, the body is actually accelerating. Now you would say, well, how on earth could it be accelerating if it's going with constant speed? But what you have to understand is that it can be going at constant speed, but it's changing direction. And a change in direction is really a change of velocity. So you can have a body, it's moving with constant speed, yes, but the fact that it's changing direction as it moves, it's really accelerating, right? You get that? So for a body going around in a circle, even though it's moving with constant speed, it's actually accelerating, right? Now, we just learned from Newton's laws of motion that for a body to accelerate, you have to have a force. See? You have to have a force, and that's the force here. Centripetal force. That's the force that is actually causing this body to move in the circle. Because if it wasn't for that force, this body might as well move off at a tangent, right? If it's here, it can very well move off at a tangent. But it is this force, sorry, it is this force, the centripetal force, that keeps kind of tugging at this body so that it doesn't move off at a tangent, but it takes the path of the circle, right? So you learn a couple of things there, that a body, even though it's moving at a constant speed in a circle, it's really accelerating. Why? Because it's changing direction. One direction changes, the body is actually changing velocity, therefore it's accelerating. And the force that is required for that acceleration is what we now call the centripetal force. And there are ways of quantifying that and so, right? Yeah. We're telling you some things about the centripetal force. For uniform circular motion, it's going to be constant. It's always acting along the radius. It's directed towards the center, right? Those are some basics of that centripetal force, right? There's a counteracting force. If you study physics to another level, you'll hear about the centrifugal force. Let's not get into that. But now, how do we quantify the acceleration and the force that causes the circular motion? Well, the acceleration, I'll go backwards. This is the acceleration. It's equal to v squared over r. Let me give you that force. In terms of, the acceleration in terms of omega. Remember I talked about omega being the angular velocity. I think I mentioned that earlier. So your acceleration will be equal to r omega squared, right? And the force, the centripetal force, is equals to mv squared over r, right? And we can actually write that now in terms of, what's here? We can write that in terms of this, right? So it's going to be equal to m r omega squared, right? What we're doing, we're replacing v squared over r, right, with r omega squared, right? Let's keep that in. So the acceleration of the body, if it's going around in uniform circular motion, is equals to v squared over r. And the v squared is really the linear velocity at a particular point, right? The force that is going to keep it moving in that with that constant speed in the circle will be mv squared over r, right? The m and the a is v squared over r. Written a different way, right? We can write it in terms of the angular, right? Angular velocity is omega, right? So acceleration is equal to r omega squared. And therefore the force is going to be m r omega squared, right? Get that so far?
Yes, sir.
Here, they're telling you a little bit here, and that's all I wanted you to get really from circular motion. But these are some extra facts here, right? So if you have an object, and the mass is m, and the radius is r, right? And the force that you're swinging it in a circle, I don't know, long ago, when we were kids, right? At least I can remember, I come from a very poor family. I still am a very, very poor man. I tell you already, I don't think this country got much rich people, right? And nowhere to carry you, and that doesn't make you rich. Right? One crash up on the road there and you turn a papa just like that. Yeah. What we used to do, we used to take empty paint saucepan, those paint cans, they call it paint saucepan. Right? Just imagine I'm using the word saucepan because at that time, you had a thing used to be made of aluminum, we used to call saucepan. Right? We used to carry food inside. And because it was the same size, and so we used to call it paint can, paint saucepan. Anyway, let me say paint can. And we used to fill it in water and tie a string to it and swing it around, just like you see in the diagram. And we used to prove to people that we can swing that paint can where it's almost it's horizontal and non-water would follow. I don't know, I mean, most of your experiences on the computer and for the TV. Y'all ever did that in real life? Y'all ever did something like that? Put some water in a container and you swing it around in a circle. And the container is horizontal, so usually the water was supposed to follow, but it doesn't. And there's where we talked about, we just mentioned the centrifugal force. While F is pulling at the saucepan or the paint can, the water is exerting what we call a centrifugal force. The water and the can is exerting a centrifugal force in the opposite direction, really on the person who is, holding the string and swinging it around. Yeah. Anyway, they're showing you that, okay, if you were to double the force, right, then the centripetal force is doubled, right? And you can check means to the speed you will be able to spin it around with. That is definitely going to increase. If you were to increase the mass, right, therefore the centripetal force will have to also increase, right? And they're showing you here that really that force is proportional to the mass. It also has a relationship to the velocity as well, right? You see? Oh no, okay. In this slide, they're experimenting with the force and the radius, right? So the bigger the radius, the less the force, right? As you can see, F is proportional to 1 over R, right? And then I think the next slide, they should actually show you that it's proportional to V squared. The force is proportional to V squared. So the more you increase that force, you can actually increase the velocity, right? Not by much though, because if you notice, yeah, V will be very small when you find the square root of it. It will be square root of the force. So that formula I gave you, right? Let me just write back the formula, just in case. We got what? Let me see, there is a blank. See, there's a blank. Look long. F is equals to mv squared over r. So force is proportional to m and v squared, but it's inversely proportional with r, right? And that's what they're showing. If F is proportional to the mass, if you have a certain mass and you double it, this got to double, right? If you don't double the mass, but you double the force, what would happen is you're going to increase the velocity, right? If the mass remains the same. If you want to double the mass and you want to keep maybe the velocity the same, well, you have to do something to that, right? So that's something worthy of your investigation, right? And similarly, we have the relation F is inversely proportional to R, or F is proportional to 1 over R. So the more you increase the R, the less the needed to spin the thing in a circle. Again, if you were a kid like me and playing around with that sauce, but if your string is long, you don't need so much force. But if you have a shorter string, you need a greater force, and you need to spin the thing at a greater velocity to keep the water inside. But you have to go home and do that at home, right? Don't use a paint can, that's dangerous, right? We didn't know that at the time. And that's all. Plastic was not even known much, right? If you had a plastic bag long ago, oh God, you like everybody watching you, like like how you have a cell phone now, like you have one of those latest cell phones. How people watch you long ago, you have a plastic container. Oh gosh. People want to know you is who, where you got that from. Right? But yes, you might be laughing at that. Take a nice plastic container at home, strong one, bore two holes in it, put water inside, and investigate this relationship. Investigate this relationship. F equal mv squared over r. Right? If I ask you questions in the test about it, and you don't know, you can't blame me. You need to go home and investigate this relationship with that same container, fill it with water, and vary the mass, see what happens with the force. Right? Vary the radius by using a longer or shorter string. Right? Vary the speed and see what happens to the force. Right? All of that. That's an investigation you have to do. And then they're telling you, what if the centripetal force is stopped when the body is moving in a circular path? But I shouldn't tell you this. If the centripetal force is stopped, the body moves along the tangent to the circle, right? And again, sometimes it happens with us. The twine that we use to spin the can around, twine cut. And guess what? The thing wouldn't continue going in a circle, move over the tangent and knock somebody. Big trouble now. They won't tell their mommy and daddy and licks from it on everybody. So keep that in mind, right? Yeah. And then they say if the centripetal force is stopped, the body moves along the tangent to the circle with a velocity v. And they ask the question, why? Oh, the answer, they should not, I want this not to be answered. Right? Newton's first law. Right? It's going to move with that velocity, of course, because of gravity, is going to fall to the ground also. Yeah. So that's a nice little introduction to circular motion there, right? Let me throw up maybe a problem that we can do, right? Give me a second. Can we stop this?
The 4 Newton, sir.
How much you get? How much?
64, sir.
It's 4.
6.4, yeah. Right? Yeah, that makes a little sense. Yeah. All right. Let's take another. Let's take another. So let's say you have another body, right? Going around with cell. And this body is 3 kilograms, 3 kilograms. And the radius is 0.3 meters. That's the center. So instead of giving you the linear velocity, they tell you that this thing is going wrong at 90 RPM. And this is a term you will hear in circular motion. This means 90 revolutions per minute. 90 revolutions per minute. Now, what you need to do is you need to convert this. Let's say the question asks to the force, right? Force. What's the force that will do that? What is the force that will take this 3 kilogram bomb and spin it in a circle at 90 revs per minute, right? 90 revolutions per minute. So what you gotta do, you gotta convert 90 RPM to radians per second, right? That's what you have to do. And how do you do that? 90 RPM will be equal to 90 times. Now, 1 revolution is really 2 pi, right? 2 pi radians, right? And remember, this is minute. So we have to convert it to seconds. So we got to divide it by 60, right? To get seconds, right? So this is 90 revolutions per minute. So to convert it to seconds, you have to divide it by 60. I think that should turn out to be 3 pi radian per second, right? So now you can find your force. Oh, before you can find your force, you want to go along with the acceleration is r omega squared, which is 0.3 times 3 pi squared, right? 3 pi squared. And that should give you roughly 2.7 radians. 2.7 pi squared. Let's leave it, right? Leave it like that. And then your force, then F would be equal to the mass, which is 3 kilograms. 3 kilograms times 2.7 pi squared, which pi you will use as 3.14, right? And when you multiply that here, there, you should have around 18 newtons.
Sir,
Yeah,
how we get this 3 pi again?
check now. What's your cancel that, 2 ones, 2, 3, 6, so 9 divided by 3 is 3, and this 5 go back here, right? So you end up with 3 pi. So you convert 90 revolutions per minute. And that is equivalent to 3 pi radians per second. And you use that now in this place here to get the acceleration, right? After that, you use F equal ma, mass is 3 today, right? Mass is 3, and then this here is the acceleration you get. Remember, 1 revolution is 2 pi, right? 1 complete revolution of a circle is 2 pi. 2 pi radians is 2 pi equal to 360 degrees. 2 pi radians is equals to 360 degrees. So if something revolves or rotates complete circle, right? It has actually covered 2 pi radians. Right? So 90 revolutions will be 90 by 2 pi radians. Right? And then remember, you have to change the minutes to seconds. You have to divide by 60. Oh, well, I should say, remember, I think that sounds confusing. That you have to change the minute to seconds and you divide it. That sounds confusing. I don't know if that is where you thought. Yeah. Okay. If you convert 90 radians, 90 revolutions per minute to radians per minute, right? You will get 90 by 2 pi. Right? That is radians per minute. But to change this now, remember this is like 90 by 2 pi over 60 seconds, right? Which is 1 minute. I don't know if you see that. 1 minute is 60 seconds. And that's why I divide by 60.
Sir, you can go over the force, which is equal to 3 times 2.7 pi square, how you get 80 Newton?
Yes, sir, please.
All right, let me move this aside. So you want to know 3 multiplied by 2.7 times pi square is 3.14 square. Right?
Yes.
Would that give you 80? Would that give you, this is a rough thing, right? It's not an exact figure.
Oh, yes, sir. So it's gonna be 79.8, so you're wrong the top.
Mm. Mm. Yeah, so this is basic stuff in circular motion. I'll send some more questions for you, and when we meet on Tuesday, we'll try a couple more, maybe more complicated ones that put you thinking. We'll discuss them and any other question you have, because we're gonna have a little test next week, Friday. And I might very well come up here to John's, because I think you have your chemistry in the morning. So you will just take a rest, and 1 o'clock we have a little test right up here. It'll be a written test.
What does this test consist of, sir?
Well, I haven't set the test yet, but I may have a few multiple choice. I might have something for you to write. Some short answer questions, and a little bit of calculation, of course. I haven't set it yet, but it's 20% of your overall grade.
It consists of how many questions, sir?
That's what I'm saying. I haven't set it yet. But you may
Okay, sir.
have a few multiple choice. You may have a few short answers, and you may have something to calculate. A couple of things to calculate. Not too hard.
Sir, them easy questions from the exercise.
I can't give you something that is so what would I say, involved that you can't do it in a test. I would never give you something that is extremely complex and you can't sit down in a 2-hour test and do it, right? No. I have to give you something that under ordinary circumstances you should be able to answer them. You're gonna get a few multiple choice, you're gonna get a few, as I said, short answer. You know, I can ask you basic things. Right, so know your we talked about what we did, or what was it? Fundamental units. We talked a little about motion in a straight line, free fall. We did a little bit of graphical work. What else we did? We did projectile motion. We talked about what vectors. We talked about additional vectors and so on. Then we did Newton's laws of motion, right? And then we talked about momentum and impulse. Well, we touched on circular motion there. That's basic. Yeah. All right, so we